This meeting is being recorded.
This meeting is being recorded. Okay, welcome everyone to today's seminar. We have Matěj Konečný here, who I don't know if just moved to Dresden or is in the move to Dresden.
I have moved.
You've moved to Dresden, so he's now officially in Dresden and gonna tell us something about model theory and I guess finite combinatorics, right? Something like that.
Yeah, so thank you for having me. I'm Matěj. I used to be a PhD student at Matfis, working for Honza Hubíčka and Erik Nešetřil. And in October, I started my postdoc at Dresden. I'm employed on a ERC grant, so there needs to be this whole disclaimer. And I'd like to talk today about EPPA numbers of graphs, which is a recent preparatory results which we had with David Bradley-Williams, who should be there, but he's probably lost somewhere in the buildings here. Peter Cameron, Honza Hubíčka, and myself. And so this is, most of the new results are really pathetically trivial. I chose that on purpose because I'm speaking here at Schut, so hopefully, no, that was a joke, but some of these results will really be pathetically trivial. My goal is to give you the overview of the area and hopefully advertise it as a nice area to work in. There's probably some low-hanging fruit, and I think it's nice, and even the existing results are really nice. And so hopefully some of you will get inspired to solve some of my problems. And in particular, if you have any questions, feel free to interrupt me at any point. At the worst case, I will not manage to say everything that I wanted. How much time do I have, by the way? I was told that I can speak up to 40 minutes, but how much time do I realistically have before you get impatient? Okay, good. Good. So where I was working with our homogeneous structures, which is sort of on the boundary of combinatorics, model theory, and topological dynamics, and I always say that out of these areas, I'm in combinatorics because I usually talk to model theorists or topological dynamists, and it is nice to be sort of an outsider because they are lenient, they don't ask hard questions, and they understand that you don't know everything. But now that I think about it, it doesn't really work here. Is there a topological dynamist in the audience? Good. Yeah, if there was, I had this prepared. But anyway, jokes aside, let me start with the talk. Suppose that we have a structure, and you can imagine a graph. And if we have a partial function from the vertex set to the vertex set, then we say that it is a partial automorphism if it is an isomorphism between what is induced on the domain and what is induced on the range. In particular, everything will be induced, so all subgraphs are automatically induced subgraphs. And I will not necessarily say that always. And if we have an automorphism of the structure A, which we call alpha, such that it agrees with F on the domain of F, then we say that this partial automorphism F extends to the automorphism alpha. So for example, a graph is vertex transitive if every partial automorphism with at most one vertex in the domain extends to an automorphism of the whole graph. Right? Because we take partial automorphism between two vertices, it extends to an automorphism, so there is an automorphism mapping every vertex to every other vertex. And this is the key definition of the talk, EPPA, the extension property for partial automorphisms. So if we have a structure B and a substructure A, which is induced, then I say that B is an EPPA-witness for A if every partial automorphism of A extends to an automorphism. Hello, David. Hello. Yeah, this is the David who was lost. Okay. If every partial automorphism of A extends to an automorphism of B. And if we have a class of finite structures, imagine the class, say, of all graphs or all triangle-free graphs, then this class has EPPA if for every A in the class, there is B in the class, which is an EPPA-witness for A. So we take some finite, say, graph in the class A, and then we can find a larger, but still finite graph B, such that whenever we find two isomorphic subspecies of A, then there is in fact an automorphism of B which map one of the pieces onto the other. This property is sometimes called the Hrushovski property because Hrushovski was the first in 1992 to prove that the class of all finite graphs has EPPA. This was motivated by some questions or some theorems in topological dynamics which I will not really talk about, but still, I want to very briefly mention a connection to model theory. If you want, you can sleep for the following 2 slides, and then I'll get back to graphs. And I'll be lying very, very slightly on this slide, but just a tiny bit. So suppose that you have a class of graphs or structures which has EPPA, and pick an arbitrary graph in the class. It is a finite graph, A0. So because the class has EPPA, there is A1, which is still finite, and it is an EPPA-witness for A0. And we can continue. A1 is finite in the class, so there is an A2, which is an EPPA-witness for A1, and so on. And we get an infinite increasing chain of finite structures. So we can take the union of this chain. It will very likely be a countable structure. And this structure has the property that every partial automorphism of this structure with finite domain extends to an automorphism of the structure. And this is called homogeneity. So how does one see this, right? Take a partial automorphism of A with finite domain. So since it has finite domain, it lives inside AM for some M. We use EPPA and to extend it to an automorphism of AM plus 1. This is in particular a partial automorphism of AM plus 1. So it extends to an automorphism of AM plus 2, and so on. So we get a chain of automorphism of these structures, take the union, and the union is an automorphism of M. Okay? So this is it. And let me just remark that this somehow shows that you can approximate the automorphism group of the infinite structure M by the by the automorphism group of the finite structures. And one can formalize this. Gehries and Rosendahl proved that if we have a homogeneous structure M, then the class of all finite substructures of it has EPPA, if and only if the automorphism group of M can be written as the closure of a chain of compact subgroups in the pointwise convergent topology, the natural topology. This is just to mention that there is a actually equivalent definition of EPPA in terms of topological groups of infinite structures. But this is not what I want to talk about. I want to sorry. Yes. So we have seen that if a class has EPPA, then it corresponds to a homogeneous structure. And so this, if we want to study classes with EPPA, this restricts where we want to or where we can look at. And luckily, in model theory, people are classifying these. So they take some conditions and they provide a list of all homogeneous structures satisfying conditions. And this is the list of our potential candidates for EPPA. So the model theorists provide some lists, and then we can look at them like vultures and hopefully get some nice papers proving EPPA. So for example, in 1980, Lachlan and Woodrow classified the countably homogeneous graphs. And thanks to them, one can just go through the list. There are like 5 families, and we know all EPPA classes of graphs. And they are the class of all graphs. It was proved by Hrushovski. Then classes of K and 3 graphs for some N. These were proved to have EPPA by Herwig. Then various classes of disjoint unions of cliques. This is really easy. Complements of these, that's immediate because you can just take the complement of EPPA-witness. And then the subgraphs of the finite homogeneous graphs. So there are a few finite graphs which are homogeneous, namely the 5-cycle, the line graph of K33, and disjoint unions of cliques and the complements. These were classified by Gardiner, and if a finite graph is homogeneous, then in particular it is an EPPA-witness for itself and all its subgraphs. So these are somehow special cases that one needs to not forget because they form special cases to some theorems. Good. And there are other examples besides graphs of classes which has EPPA. For example, if we fix a relational signature, then all relational structures with this signature or possibly for the cliques have EPPA. Metric spaces, 2 graphs, metrically homogeneous graphs, some generalized metric spaces, and n-partites ornaments, and groups. Groups are a very different example than all of the others, and it doesn't fit really that well into the combinatorial framework that I have or that I think of when thinking about EPPA, but it is also a nice example. And then I want to mention the sort of the OG open question in the area, and it is whether finite ornaments have EPPA. This has been asked by Herwig and Laskar in 2000. It turns out to be equivalent to some statements in profinite group profiling topology on free groups, and even though people have tried, it hasn't been solved yet. But maybe it is just like it is mostly people from model theory or topological dynamics thinking about this. So maybe it is just waiting for a nice combinatorial idea, which will prove that tournaments have EPPA or don't. Good. And now finally to graphs. So if you fell asleep, now it's a good time to wake. If we have a graph G, then by EPPA of G, we denote the least number of vertices of an EPPA-witness for G, right? So how many vertices do we need to add to symmetrize G, if by symmetrize we mean get an EPPA-witness? And by EPPA of N, I mean the maximum of this EPPA of G over graphs on N vertices. So Hrushovski in 1992, he proved an upper bound on EPPA-N, namely this 2n to n factorial, which is like doubly exponential. And he proved a lower bound, square root of 2 to the n. I would like you to think for a few seconds whether you have a guess what graphs are hard to produce EPPA for. So if you wanted to prove a lower bound, what graphs would you look at? And while you think, I just want to mention that in his paper, Hrushovski asked the question to prove the bounds. In particular, he asked whether a single exponential upper bound can be proved. And his paper, so Hrushovski is a big guy in model theory, and this paper was in Combinatorica. So I think that he just thought that if he's publishing a paper in Combinatorica, he should make it combinatorial. So he asked for bounds. I do not think that he cared about these bounds. And frankly, I have been giving this talk without the new results for several years now, and I also never cared about the bounds. Now I slightly do care, but I was giving this talk because I was hoping that if people look at it, they will identify what sort of properties are important for. What sort of properties are important for EPPA? What sort of properties are important for EPPA? Yeah, good. So are there any guesses for graphs which are hard to produce EPPA-witnesses for? So any canonical complicated graphs?
Like Ramsey graphs?
Well, Ramsey graphs. You mean random graphs? Yeah. So conjecturally, but it is hard to sort of produce lower bounds, right? So the random graphs have the bad property that they are very non-symmetric, right? They have very little automorphisms. So if you want to say that if you take two subgraphs on 4 log n vertices, then they are not isomorphic with high probability. And so you have just a few partial automorphisms which you need to extend. So on one hand, random graphs are like very random, very non-symmetric. So you need to make a lot of adjustments to symmetrize them. But on the other hand, they are really non-symmetric, and so you don't have that many partial automorphisms that you need to handle. So the say easy lower bounds are graphs which are at the same time asymmetric, because if you take the independent set, it is an EPPA-witness for itself, right? Anything extends. But at the same time, that they also need to be pretty symmetric, because you want to have many partial automorphisms. So Hrushovski's lower bound graph was the half graph. The half graph is a bipartite graph with both partitions of the same size, such that you connect a vertex with all the vertices on the other side, which are above it. It is an important graph in model theory because it gives a dividing line between the stable theories and non-stable theories. So that's like Shelah model theory from 1960s or 70s. And it has been important in combinatorics because, for example, in the proof by Lovas and also other people that the similarity regularity lemma needs to have many these partitions. The half graph is the problematic case, right? The half graph gives you this tower of twos, and it turns out by Maliaris and Shelah from 2012 or something that if you have graphs which avoid half graph, then you have very nice regularity lemma with just a few partitions and so on. So the half graph is sort of canonical problematic graph in model theory, and Hrushovski also showed that it is problematic for EPPA, even though, as we will see later, it turns out that it was just a decoy for Hrushovski. So in the original version of the talk, I would then say that maybe this has something to do with model theory and there's something deep. But now I'm foreshadowing. It turns out that this is not the case. But first, I would like to overview the upper bounds, and there are more or less two upper bounds since Hrushovski's paper that one needs to talk about. One was given by Herwig and Laskar, and they proved that if you have a graph on n vertices at maximum degree delta, then there is an EPPA-witness on delta n choose delta vertices, which is in n to on. But in particular, if delta is a constant, then you get polynomial EPPA-witnesses for bounded degree graphs. And the other upper bound was by David Evans, Honza Ubichka, Jarek Neshetsian, and myself, where we were able to construct EPPA-witnesses on n times 2 to n minus 1 vertices. And these two are sort of the best bounds that we have by now. Our bound is better sort of universally, and the Herwig-Laskar bound is better if you parameterize by the maximum degree. And on the next two slides, I will give you sketches of proofs of these theorems. My goal is not to fully convince you or fully explain to you these proofs. My goal is to show you that I think that they are simple enough to fit on two slides. And if you are interested, there are references. There are essentially the proofs in our paper that I was citing on the first slide, so you can look at it. They are really easy, but perhaps they might need a little bit of pondering to persuade yourself that things really work. So for the Herwig-Laskar, we have a graph G, and we want to construct an EPPA-witness on delta n choose n vertices. And this EPPA-witness will be the complement of the Kneser graph. So suppose that G has vertex set V and edge set E. And for now, suppose that it is delta regular. It will make things easier. And we will define graph H such that its vertices are all subsets of edges of size delta, and two subsets are connected by an edge if they have non-empty intersection. So first, we need to find a copy of G inside of this graph, and this we do just by sending every vertex to the set of edges incident with it. This is where we are using regularity, because every vertex needs to be sent to a set of size delta, right? And now, if we have an arbitrary permutation of the edge set, then this is an automorphism of G. That's easy because non-empty intersection is preserved by permuting edges. And so now a partial automorphism of G gives us a partial permutation of edges. And if we are a little bit careful, we can extend it to a permutation of edges which respects this partial automorphism, and we are done. And if G is non-regular, then we can just add half edges to vertices to make it regular, to make all these sets have the correct size, and we are done. So this is the first upper bound. If you talk to Wojtaredl about EPPA, then he gets angry that it is even a theorem of Hrushovski because he sees this immediately. For me, it took some time to understand, but I think it is very nice and simple. And the second construction by David, Honza, Jarek, and myself is the following. Fix a graph G, maybe this one, and we'll again define graph H explicitly. And the vertices of H will be sort of in groups. Every group will have a projection to a vertex G, and every member of group will have an opinion about all the other groups. So formally, the vertices of H will be pairs V, which is the projection, a vertex of G, and F, which is a function from all the other projections to 0, 1, which will be the opinion. And so for example, this graph has projection V3, and its opinion about V1 is 1, and its opinion about V2 is 0. And this vertex has projection V1 and some other opinion. And we define edges. We put two vertices to be an edge if and only if they have different projections, and their opinions about each other are different. So they disagree about the projection of each other. Why not? So if the definition is not clear, then maybe it is clear from the picture what the edges are. And again, now we have we have defined the graph, and in order to make it to show that it is an EPPA-witness for G, we need to find a copy of G in the graph. So how do we do it? Well, maybe before I show you the copy, it is yes. So this graph has n times 2 to n minus 1 vertices because there are 2 to n minus 1 opinions for every projection. And now we want to embed G inside. Since you guys are doing more computer science, then I can say here just that this graph is sort of universal for online embeddings, right? If you have a graph on n vertices, you enumerate it and you just put the first vertex anywhere in the first column. The second vertex you can put into the second column and pick opinion correctly so that the edges to the previous vertices are as you want, and so on. So this is very universal for online embeddings. But formally, one can pick an embedding by sending a vertex to have the projection itself, and the opinion has non-zero exactly about its smaller neighbors. This is sort of the asymmetric variant of the adjacency matrix, and this works. And now we want to show that H extends partial automorphisms of G. So maybe pick this partial automorphism. We can project this partial automorphism down to the vertex set of G and extend it arbitrarily to a full permutation of the vertex set of G. And this permutation gives us an automorphism of H by permuting the columns and permuting the opinions accordingly. For example, we would flip these two vertices, and this third vertex needs to go somewhere. It needs to go somewhere in its own column because we extended it, and it needs to have an edge to this one and not have an edge to the upper one in order to extend the partial automorphism. So what do? We just tell him to change his opinion about the other two columns, and we are done. Formally, we have two types of automorphisms of H. One is given by a permutation of the projections, and the other is given by a flip. So what is a flip? We pick two projections and tell all of them to change their mutual opinion about the other projection. And this is done. Let me just remark that this can be straightforwardly generalized to hypergraphs and arbitrary relational structures, and one can even add unary functions. The hypergraphs will be useful later if I have time. Good. So just to sum it up, these are the upper bounds that we have. We have finite homogeneous graphs. That's the 5-cycle line graph of K33, disjoint union of cliques and the complement. And these are EPPA-witnesses for all of their subgraphs, and one needs to keep them in mind if you want to say something general, right? Because if you want to say that EPPA-witnesses are at least quadratic, that this is not true because C5 or n times k mn are EPPA-witnesses for themselves. So you need to always exclude finite homogeneous graphs. Then we have the Hervé-Klaskar construction, the complement of the Kneser graph, and they have this size. And finally, we have what we call valuation graphs, and they have this size. So these are upper bounds. Are there any questions? Good. So now let me go to lower bound. Up until a month and a half ago or something, I would just say that there's this half graph, and maybe it has something to do with model theory and stability, and that would be it. And I have done that a few times. At one talk, David and Peter got interested and started studying EPPA numbers using permutation group theory, which is like hard work, not what I'm doing here, but real mathematics. But I was last time I wanted to give such a talk was 2 months ago, and with Honza on the train, we decided to give it a little think, and we realized that Hrushovski was looking at the decoy graph, and that actually there is a much simpler graph which is much harder for EPPA. And we produced a hard graph whose EPPA-witness is at least 2 to the n divided by square root of n. And the proof is basically by Hrushovski's argument. You just use it in a simpler way on a simpler graph. And the graph is the following. It has 2 parts. One part has n vertices, the other part has 1 vertex, and this vertex is connected to half of the vertices in this part. First, notice that every permutation of the left part is a partial automorphism of this graph. Well, obviously, because it is an independent set. And I claim that in every EPPA-witness of this graph, whenever we pick a subset of half of the vertices of the left partition, there will be a vertex which is connected precisely to this subset and not to the rest of this partition. So how do we do it? We pick an arbitrary set, and we define a partial automorphism which sends the neighbors of this vertex to the element of this set. We complete it to an arbitrary automorphism of the left part, and because we have an EPPA-witness, then we ask for this partial automorphism to be extended, and this extension needs to send this vertex somewhere. And where does it send it? Well, it needs to have edges precisely to those vertices in S, because that's how we picked it, and non-edges to the rest of the left part, and then we are done. And since there are n-choose and half subsets of size n over 2, by some standard asymptotics, we get the lower bound. And so this is it. That's like the lower bound. One can use this idea to prove some other lower bounds. So for example, if you have a triangle-free graph with maximum degree delta, which is constant, then we get n to the delta lower bound. And as a corollary of this, we get that cycles have quadratic EPPA numbers because the upper bound is given by the Kneise graph. So I will just give you a picture of the proof for cycles. For the general case, it is the same, right? So you have a cycle, use the greedy algorithm to find an independent set. Since it's bounded degree graph, the independent set is linear. And then you will find a vertex, which is connected to, in this case, 2 members of this set. So you have a large independent set, vertex connected to 2 of them. So in any EPPA-witness, there will be a vertex connected to exactly every pair of this independent set. And you get a quadratic lower bound. One can do more with this idea. One can prove that asymptotically almost surely the Erdős-Rényi random graph has superlinear EPPA numbers. And I will just give you a sketch because I don't like computation. So first, it is a well-known fact that the random graph has independent set of size 2 log 2 of n. Then you can find a vertex which is connected to roughly half of this set, and you do the same argument that we did before. This is not actually true because you don't get exactly half of the set and so on. So you lose something, and depending on how careful you are with the computations, you lose more or less. So in the paper, we prove 2 to n minus epsilon for any positive epsilon. And once again, the same argument but I think that this is a stupid lower bound. I think that actually the random graph has a much larger lower bound, but it seems that finally it seems that a new idea will be needed to prove this lower bound. So the reason why I'm relatively excited about our stupid results and why I'm giving the talk is that I'm hoping that in order to improve them, one will eventually need to have an idea, have a real idea, and that the idea will teach us something about why EPPA is hard, and or what makes EPPA hard or easy. And I'm hoping that by seeing this, it will enable us to solve some longer-standing open problems in the area, like EPPA for tournaments or some other EPPA classes, or some other classes for which EPPA has been open. So that's my hope. And so here, you are not going to get a larger independent set than 2 log n. So one needs to do something else. One idea might be if you have a graph G and you have an EPPA-witness, then every vertex of the graph has the same degree in the EPPA-witness, because you can send every vertex to any other vertex via partial automorphism. And similarly, if you have a non-edge of your graph, then the endpoints will have, or every pair of endpoints of a non-edge will have the same number of vertices in the intersection of their neighborhoods. Similarly for edges and so on. In general, if you have 2 parts of your graph which are isomorphic, then the EPPA-witness looks the same from their point of view. And maybe if one is careful, one can make a computation for the random graph showing that it is hard to somehow symmetrize, to regularize graphs. It is not hard to regularize vertices. You just need, like, by law of large numbers, like square root of n vertices roughly to add. But maybe it is harder to symmetrize non-edges or triples or something. I don't know. So I haven't been able to make this idea work, but I also cannot compute. And final iteration of this observation: if you have constants c and d, then the sparse random graph with parameter c over n has super polynomial EPPA numbers. And how do you do it? Well, you find a linear size independent set. How do you find it? These graphs are around where the large component appears. In particular, a linear part of the graph is still a forest, and you just take the leaves of the forest, and you get a linear size independent set. And now you compute that that for every constant d, there is a constant probability that you will find a vertex connected exactly to the members of this independent set, and you do the same argument once again. Good. So to sum it up, we have a lower bound for EPA number, which is almost matching. There is like n to 3/2 difference between the lower and upper bound. Then one argument that I have not talked about, because it is actually more involved, is that if your graph is not a subgraph of a homogeneous graph, then one can prove that every EPPA-witness of G needs to have at least 5/4 n vertices, which is really like pathetic, right? This says that you need to add at least a little bit something, but it feels like actually you need to add much more, right? We conjecture that at least a lower bound of quadratic holds, right? And to prove this is not easy actually. It uses some finite permutation group theory and some classification results. So unlike all the other bounds, this actually has a mathematical content in it. Then we have seen that if you have a triangle-free bounded degree graph, then we actually know the asymptotics of the EPA numbers. They are polynomial. We have seen a lower bound for the random graph. We have seen the lower bound for the sparse random graph. And I haven't shown this, but it is yet again the same idea. If you have a bounded degree graph, which is not a subgraph of a homogeneous graph, then actually one does get a quadratic lower bound. So in sparse graph or very dense graph, because things complementation behaves nicely with respect to EPA. So for sparse graphs, we understand the situation more or less. But as soon as your graphs are not bounded degree, then these methods cease to work that efficiently. But it feels like it should be harder in a way to make EPA-witnesses for graphs with large degree. But yeah, good. And if I have a bit time, I want to just briefly talk about hypergraphs because there the situation is there is much less known. So with Honza and Jarek, we can construct EPA-witnesses which have this size, where EPA k is the uniformity of the hypergraph. So in particular, if you pick k equal to 2, then you get the EPA-witness that I have shown. And the obvious generalization is the one that one uses here. And in the paper, we were able to construct a 3-uniform hypergraph on this many vertices, which has at least n factorial. This should be 2 to n factorial. That was a mistake. There should be 2 to n factorial EPA numbers. Good. And so how does this graph look like? What does it look like? It is a tripartite, one partition of blue vertices. They are just labeled by numbers from 0 to 2m-1, or maybe you can imagine like binary strings of length m. The middle part, which should be red, is labeled by numbers from 0 to m-1. And the last part has just one vertex, the pink square. And we put a hyper edge AB pink square if and only if the bth bit of A is equal to 1. And now, and I will just skip through this. If we have an EPA-witness for this graph, and we pick an arbitrary vertex of this EPA-witness and a blue vertex, then this arbitrary vertex of the blue of the EPA-witness gives us a binary string for A just by looking at in which hyperedges this arbitrary vertex A and the members of B are. So in particular, if we pick the pink square, then we just get the identity. And I claim that for every permutation of the left part, there is a vertex in the EPA-witness which gives us such a function. And how does one do it? One just permutes the blue vertices according to the permutation, fixes the red vertices, and sees where the extension of this partial automorphism sends the pink square. And consequently, we get this lower bound. So again, there should not be m factorial, but 2 to n factorial. Let me just remark that in total, if you just have a set, then there are just 2 to O n log n partial automorphisms. So this is the best that one can do by this kind of argument, right? Because for every partial automorphism, we are able to get one vertex in the EPA-witness, and there are not more partial automorphisms than we are using. So in order to improve the lower bound for 3-uniform hypergraphs, one would need to again do something more. And I would like to see anything that does more than this. Good. So to conclude and to give you all the open questions, one problem is to close the gap for EPA numbers of graphs, where I doubt that the lower bound is tight. I actually think that the graph that I showed you, the star with a large independent set, has larger EPA numbers that I proved, because I did not talk about any partial automorphisms which flip the right vertex, the one which has actually many edges, which send it to the left part. So you can send the right vertex to the left part and then still permute many of the vertices of the left part, and these are still partial automorphisms, and they make the EPPA-witness to have more structure than what we have actually proved. I tried a little bit thinking about that, but I was not able to make things work. But I think that there is room for improvement, and I'm not convinced that it should be like that hard to improve the lower bound, at least sort of. On the other hand, the upper bound, even if somebody was able to improve it by 1, it would very likely be interesting. I convinced myself that unless your graph is an independent set or something, that you actually do need the whole graph to extend partial automorphisms, that you cannot do any cheap tricks like taking a subgraph of the graph that we constructed and proving that it still works. But maybe I'm just stupid. Another, so the conjecture, I've already mentioned this. We conjecture that if you are not a subgraph of a homogeneous graph, then you have actually quadratic EPA numbers, or at least quadratic, but even proving something superlinear here would be really nice. And it would need some new ideas, because it would in particular talk about all dense graphs where finding a large independent set just does not seem to work. Then I already hinted at this question. We have polynomial EPA numbers for bounded degree graphs and bounded codegree graphs. So the question is, are these the only graphs with polynomial EPA numbers? Oh yeah, and you need to again think about the subgraphs of homogeneous graphs. And here I don't know, and this would need a new proof of an upper bound. And finding the lower bound is relatively simple, but finding the upper bounds, like once you know them, they are not hard to prove that they work, but coming up with the upper bounds seems to be relatively complicated. Good. Here I should mention that David and Peter have a small family of upper bounds which are sort of related but not completely, but they work only for very particular classes of graphs. So there are some preliminary results, but nothing that would be able to solve these questions. Good. Then a problem: improve the bounds for the random graph or some other distribution on graphs. Then a nice problem might be to improve the bounds for planar graphs, because planar graphs have large independent sets and large degrees. So maybe things should work there, or sorry, large independent sets, and at the same time they have small average degrees. But yeah, I was not able to make anything work. And another problem is to compute the exact EPA numbers of cycles, but here we call dips. And Peter is claiming that he can compute those, and actually the Knaser graphs should be the optimal EPA-witnesses. But this seems to be hard to prove, and it uses a lot of permutation rule theory. So maybe compute the exact EPA numbers of other graphs. Peter and David have some very small cases using computer. Then one can study EPA numbers of directed graphs. A lot of things generalize there from graphs, but not everything. Then obviously the hypergraphs, that will be nice to understand. And oh yeah, let me skip this because I see that Tomáš is standing.
Giving you have 1 minute.
Okay, good. So we have seen that KM3 graphs are one of the homogeneous graphs, so it makes sense to ask EPA for them, and it is known that they have EPA. So if you have a triangle-free graph, then there exists an EPA-witness which is triangle-free. But these EPA-witnesses are much larger than the one that we have produced. In particular, we have a construction which is doubly exponential, and it would be nice to understand this. We have no lower bounds besides those that we have. So yeah, there might be some relatively easy results here. And finally, the question of Harry Glaskar, whether finite tournaments at EPPA. Good, and that's it. Thank you.
Any questions? I have too many, so I will give the floor to anybody. No, so I mean, what happens if you look at, let's say, groups or monoids and do the same kind of thing? You know?
So group Z EPPA, because you just embed into the symmetry group.
Yeah, but with the approximations from top or bottom.
What do you mean approximations? Oh, bounds.
Bounds, yes.
I don't know anything about it. You can prove something about it.
No, well, I just occurred to me because you mentioned using computers, but actually for counting the number of monoids of some size or something, there's a lot of tools you can use that help you. Generating algebraic structures is, I guess, quite simple. So you can do that if you want. I can give you hints.
But there's a lot of them.
Yeah. Whenever you say it's subhomogeneous, you mean a substructure of a finite homogeneous.
Yes.
And no. Okay. And can you look at classes abstractly? So you would do like I have a class which has JEP or AP. What's the EPPA number? Of course, that's nonsense, but maybe you can put some kind of if you know the JEP has some upper bound on, like, if I give you two structures, the one you embed into is bounded by this function or something like that. Can you then?
I mean, think about tournaments, right?
I can't.
EPPA for tournaments is open, but all these problems that you are, or all these things that you are suggesting seem to be trivial for tournaments. The issue with tournaments is that the tournaments have no automorphism of even degree, right? Because you have an orientation of a pair. So if there was an automorphism of even degree, by taking powers, you would make it into something which flips a pair, and that would not be an automorphism of tournaments. And all these constructions that we had really heavily used with the fact that you have non-edges there, and so you can flip things. So for tournaments, it seems to be more of a group theoretical problem than a combinatorial problem. But at the same time, maybe it just needs a smart combinatorial idea. I don't know. But thinking, yeah, anything that fails for, if you want to do things abstractly, then you had better make sure that it doesn't involve tournaments. Thank you for having me.
If no more questions, then please.